So we've looked at permutations where we care about the ordering of elements in a sequence. Now let's look at combinations, and that's where we don't care about the ordering now. We just care about the number of different ways we can do things. So an example, suppose we've got 5 letters, A to E. How many ways can we draw 3 letters from that? So for example, we could draw AB. Suppose we had the letters ABC. We could write them as ABC. We could draw the A first, and then the B, then the C. We could have the A, then the C, and so on. But that's just ABC, right? We're going to treat all of those as the same. We're not interested in the ordering of these. So how many ways can we draw 3 letters out of 5? So we know that there's first of all, if we do care about the order, how many ways can we draw them? So there's 5 ways to select the first letter, 4 to select the second letter, 3 to select the third letter. So there's 5 times 4 times 3, 60 ways of taking 3 letters out of 5 where we care about the ordering. But we don't care about the ordering, right? So if we have a look at this ABC example, we can count them up. There's 1, 2, 3, 4, 5, 6 different ways we can write our 3 letters there. So we divide our 60 by 6 to get the number of groups when we don't care about the letter order. See, we're using our division trick again. And so what we have is essentially a variant on our permutation problem, right? So we've got, if we're drawing 3 letters, there's 3 factorial ways we could write out our 3 letters. So that's our 6 permutations. And so the number of groups not caring about the ordering is going to be the 5 times 4 times 3, which is the total number of ways we can draw 3 letters out of 5 where we care about the ordering, and then divide through by 3 times 2 times 1, which is the number of different ways we could order 3 letters, but we don't actually care, so we divide that out. We lump all those together. And so writing that more generally, that idea more generally, is going to be, if we've got n items and we draw k out of them, so think of it as a bag with n things in them, n different things, and we're going to draw k of them out. The first item we draw out of the bag, there's n different items in the bag, so there's n different ways we can draw the first item. Now we've taken one out of the bag, there's only minus 1 left. So the second item we can only choose n minus 1 different ways. Third item now it's n minus 2 down to n minus k plus 1. And then we multiply them all up with the product rule. That's the number of ways we could draw k items out of n where we care about the ordering. But we don't care about the ordering. So these k items themselves can be organised k factorial different ways. Whether we picked an A, a B and a C, or a B, a C and an A, we don't care, they're all the same. So we divide through by that. And so the general rule is we've got n minus 1, n minus 2 down to nk minus 1 is the number of ways we can pick the items caring about ordering. Then we divide through by k factorial, so we clump together, we treat all the ones with the same, regardless of the ordering, the same 3 letters to be the same. And there's a nicer way to write that, which is equivalent. So if we write this n factorial, so that means n, so we keep this product going down, so instead of stopping at n minus k minus 1, we go n minus k, n minus k minus 1 down to 1. And then divide out, it turns out that bit at the end here that I've just, is n minus k factorial, right? If you just write it out. So a clean way to write this is n factorial over n minus k factorial times k factorial. These are the same, that equals means they're the same. And this combinations happens, we're going to come across this so often, it's got its own special notation, which is you write it with big long brackets, you put an n at the top and k at the bottom, and the way you say it is this is n choose k. So this n above the k with big brackets is n choose k, and it's equal to this formula. And we have a couple of conventions. So we say 0 factorial will define to be 1, just so the numbers work out. It's a bit strange. So the n choose 0 is 1. There's one way to choose nothing out of it. So it's like the empty set. And n choose n is 1. So it all makes sense. Let's look at some examples. Suppose we have a byte, so 8 bits, and 3 errors can occur. How many different ways can 3 errors occur? So it's 8 choose 3 is 56. We're done. We have 100 servers. We want to pick 50 from them. How many ways can we pick 50 servers from 100? 100 choose 50. It turns out to be 10 to 29 or thereabouts. We have 6 pizza toppings. We want to select 4 out of them. How many different pizzas? 6 choose 4 is 15. Lottery numbers, 47 choose 6. It's about 10 million, 10, 11 million. Okay, so this is when, now we'll make things a little bit harder. So suppose we've got our 6 toppings, but now we add some constraints. And this is when the counting, so far the counting's been pretty straightforward, right? This is when it starts to get harder. And and you can make it really quite hard. These calculations, these calculating, accounting, you can make it really quite hard by adding different sorts of constraints. So I'm not going to be making it hard in this course, nothing harder than what we're talking about, but already going to be talking about now, but it's already quite hard actually. Okay, so how to deal with constraints. So here's the example we've got. Suppose these are our 6 pizza toppings. Suppose Gorgonzola and Epoise, these are 2 well-known smelly cheeses. Suppose there's no way you're going to put 2 really stinky cheeses in the same pizza. It would just be, you don't want to be in the same room as it, let alone put it in your mouth. So we've got a constraint. You can only put at most one of those 2 cheeses on your pizza. Well, now how many different ways can we how many different pizza toppings are allowed? Well, we know that there's 15, 6 choose 4 in total, but now we've got these constraints, so it makes it much harder. So there's 2 ways, two strategies for doing the calculation. And which one is best depends on the nature of the problem, the nature of the constraints of the problem. So you have to stop and think. So I'll show you both methods. And in this case, both are kind of similar, but in general, when you'll see in the weekly assignments and so on, you have to, if you find one way is turning out to be really hard, try the other one, right? Because I'm not going to be asking you to do anything really hard. If you find you're doing these calculations of counting and it's like a nightmare, that means you've done it wrong, right? Because I'm not giving you things that are nightmarish to calculate. Try the other way. Have a stop and have a think, right? You do have to stop and have a think with this counting stuff once you get beyond the really simple examples. Okay, so here's the one strategy, first strategy. So we considered the possible cases. Essentially, we're doing a kind of enumeration of the possible cases. So what's possible? We could have Gorgonzola and 3 other toppings, but we can't have the Epoise one, right? So that means, remember we had 6 toppings in total. Once we exclude Epoise, there's only 5. We've already got Gorgonzola, so there's only 4 left. So this is choosing 3 other toppings from 4. 4 choose 3. It's 4 choose 3 ways of having Gorgonzola and 3 other toppings. Epoise and 3 other toppings, exactly the same, 4 choose 3. And the third option is that we have no cheese, right? We just have 4 toppings that aren't cheese. Now, remember we had 6 toppings. If we remove the 2 cheeses, there's only 4 toppings left. So we have to, it's 4 choose 4. And then we just add them up. That gives us our 3 different sets of options, and that gives us 9. Now, when we can enumerate the settings, so it's just 3 here, and it's not too many, then this is a reasonable strategy. But if the constraints mean that this kind of enumeration there's a lot of these and it's getting messy, maybe you should think about this second strategy. And here we're going to do a subtraction. So there's 6 choose 4 ways, ignoring the constraints, that we could choose 4 toppings out of 6. Now let's calculate the ones that aren't allowed. So we know that Gorgonzola and Epoise, so the 2 cheeses together, plus 2 other toppings is the set that aren't allowed. Now remember, we've got 6 toppings, we take the 2 cheeses so that means there's 4 toppings left, and we're going to choose 2 from that 4, so it's 4 choose 2. So there's 4 choose 2 different ways of choosing banned toppings. So then we take the total number, 6 choose 4, subtract off the banned ones, and we get 9. And so you can see actually in this case, this is the simpler thing to do, it's just the one step, we subtract it. But both are quite straightforward in this case. But keep an eye on the fact that both strategies are possible, and you need to apply a bit of strategizing about which one to use in a particular example. And I'll just finish by mentioning, talking very briefly about power sets, more just as a digression so you're aware of it. It's something that won't come up too much, but just so you're aware of it. So what's a power set? It's a set of all subsets. So for example, suppose we've got the set ABC, then the set of all subsets, we always include the empty set. It's the set of individual elements, A, B, C, the set of pairs of elements, A, B, A, C, B, C, and a set of all three, right? That's a set of subsets. And we write it as 2 to the S for reasons that will become clear shortly. So how many elements are there in that set of subsets? Well, there's 3 choose 0, that's the empty set, we picked nothing. 3 choose 1, that's the set with 1 element. Set of subsets with 1 element. 3 choose 2 is set with 3 elements. 3 choose 3 is set with 3 elements, and we add them all up. And so that there's a general rule for that. If we're going to sum n choose k, and k goes from 0 to n, right? So that's the size of that set. Now this is a bit of notation here. That sigma there, that's a Greek sigma, stands for sum. It's a shorthand for like a for loop, where we take k goes from 0 to n, going in steps of 1. Okay, so k is going from 0, 1, 2, 3, 4 up to n. And then we're adding up the elements. So this notation here is a short way of writing n choose 0 plus n choose 1 plus n choose 2 plus n choose 3 up to n choose n. And here n is the size of the original set S that we're shown. With ABC it would be 3. And it turns out there's a thing called the binomial theorem that you don't need to remember. I'm just including it for just for general knowledge, really. We won't be making much use of it. That this sum is equal to 2 to the n, right? So you can see the notation. So 2 to the s is equal to 2 to the n, where n is the size of the set S. And we're getting it by counting all these combinations. So it's just quite a nice bit of trivia to bear in mind.